As I think I announced previous week, that so we are going to have a second quiz on 28th, right? 28th May. So previously we considered the inhomogeneous differential equation of the form px dx squared d square y qx dx dy rx y is equal to s of x. And I told you that on the right hand side is sometimes called the source term. So the first step of the solution is to find the solution for the homogeneous equation first, right? Step number one, find solutions of px dx d square y qx dx dy plus rxy is equal to 0. So let's say yh1x, yh2x, then the particular solution, say ypx of equation 1 can be written as ypx is u1x yh1x plus u2x yh2x. That means we can represent the solution of the inhomogeneous differential equation as the combination of a homogeneous solution yh1 and yh2. The difference is the coefficient u1 and u2 are also function of x, right? And I'm not going to repeat the procedure that we covered last week, so just summarize the result. Then u1x can be written as minus over wx px prime sx prime yh2x prime dx prime. This is an indefinite integral. Indefinite integral is called 부정적분, right? Just function of x. And u2x is wx px prime s of x prime yh1x prime dx prime. And this is called Wronskian. Is yh1x yh2x dx dyh2x 1x dx dyh2x is called Wronskian. Its name. And wx is not equal to 0. That means if the Wronskian is 0, then this approach fails. Then you cannot find a solution in this method. But the case we are considering is mostly is not. So then the general solution is the following. C1 yh1x C2 yh2x plus u1x yh1x plus u2x yh2x. So these are particular solutions. Of course, you can have a similar approach for like a third order differential equation and higher order differential equations. But let's just focus on the second order differential equation for this method. And you can actually use a general similar method to obtain for the higher order differential equation. But for now, I think for you, maybe you can just focus on for the second order differential equations. Otherwise, it's going to be too difficult. So for you. So let's consider some examples. Let me see. Just in case I copy the example. All right. X. So this is a typical equidimensional differential equation, right? So step number one, you find the homogeneous solution. Let me see. Step number one. X squared dx squared d squared y minus ey is equal to 0, right? So this is typical equidimensional ODE. So idea is using the following form: yx is something like y of zx, and z is log x, same as logarithm natural x. Then we can transform the equation as follows, right? dz d minus 1 y minus 2y is equal to 0, right? So dz squared y minus dz dy minus 2y is equal to 0. And y, we can trial solution, lambda z. And then lambda square minus lambda minus 2 exponential lambda z is, you can factorize lambda square minus lambda minus 2. It can be easily done, right? That's the middle school problem. Lambda plus 1, lambda minus 2, exponential lambda z is equal to 0, right? So, do you think I'm going a little bit too fast? It's okay? So you must be quite familiar with my speed by now. That's good, right? Good sign. So lambda is minus 1, 2. So yh1x is exponential lambda log x is 1 over x. yh2x is exponential 2 log x is exponential log x squared. This is natural log, of course. So in my class, unless otherwise specified, I'm just meaning log is ln. Unless I specify the base, like log a. Otherwise, it's just we just presume that the base is e. So x squared, right? So Wronskian x is 1 over x. If we differentiate 1 over x, what do you get? Minus 1 over x squared, right? Minus 1 over x squared, 2x. So it's 2 plus 1 equal to 3, so it's not 0, right? And of course, we have px is x squared. Wronskian is 3. So we have px is x squared. Wronskian is 3. S of x is x, right? So u and yh1x is 1 over x. yh2x is x squared. So u1x is minus over wx prime, px prime, s over x prime, and yh2x prime dx is minus over Wronskian is 3, x squared, x prime, yh2 is what? X prime squared dx prime, right? So this and this cancels each other, and we have minus 1 over 6 x squared. u2x is wx prime, px prime, s over x prime, and yh1x prime dx prime is 3x prime square, x square, and 1 over x prime dx prime is, this cancels each other, minus 3x over 1, right? Therefore, particular solution is u1x, yh1x, plus u2x, yh2x is equal to minus x squared over 6, x 1 over x plus, actually minus 1 over 3x over x squared is equal to minus x over 6 minus 3 over x, right? So 1 over 6 plus 1 over 3 is what? 6 over 2, 3. Minus x over 2, right? So particular solution is where is the space? Maybe here. 1. So this is 1, 2, 3, 4. So general solution yg c1x minus 1 plus c2 x squared minus x over 3. So this is the solution for that equation. Since I covered a little bit fast, maybe I'll let you have the time to copy the screen. And there is another method for solving inhomogeneous differential equation if the coefficient is constant, much easier than the other way. So I'm going to cover a new topic called the Laplace transformation. So let me just ask you a question. How many of you are taking a class on the electric circuit? 전기회로. And so you are learning Laplace transformation or you have learned? You have, so Laplace transformation is not covered yet, right? Okay, so it's probably about a good time to study that beforehand. And how many of you are also taking electromagnetic theory? No? That's for second semester? 전자기학. It's probably for second semester. All right. Because I'm going to cover the vector analysis after Laplace transformation. The new chapter on Laplace transformation. That's the definition of a Laplace transformation. It's actually one of the integral transform. It's one of the it's also one of the easiest way of solving inhomogeneous differential equation with the constant coefficient. Also, one of the convenient method for solving inhomogeneous ODE with constant coefficient. So usually we define the following. Y over t dt. then so what is the different Laplace transformation of the first order derivative? Which is same as this. You differentiate the whole thing. Minus right? So differentiation of yt multiplied by exponential minus st and you integrate over is the same as you differentiate the whole thing minus you differentiate the first term, right? So this is same as this. And actually you have learned this in your high school days. Well, by partial integration, 부분적분, right? It's one of the first example in, I think, 수학의 정석. So how many of you have studied that 수학의 정석? Raise your hand. Just one? I see. So it's not very popular reference book for your times. So what is the most popular reference book? 수학의 개념 원리. 개념 원리 is one of the most popular reference book for your times, right? Nice. How about 해법 수학? Anybody who has studied that book? Raise your hand. None? I see. So, I see. I was in high school in 1976. So, probably you were not born then, right? And maybe even your father and mother was not born then. At that time, right? So in 1970s, I think the 수학의 정석 and the 해법 수학 was too popular, the reference book for the mathematics. So I think, but probably it's the same, they cover the same material anyway. So let's save some space here. So then it becomes exponential minus st y of t 0 to infinite and minus of what happens if you differentiate exponential minus st by t? You have minus s, right? So you have minus s exponential st y of t dt is s of y of s minus y of 0. can I move on? Okay. So we defined Laplace S of yt as integration from 0 to infinite to minus st yt dt, as we denote this capital Y of S. Then the Laplace transformation of the first order derivative y over s minus y over 0. How about this? Second order. It's the same as this, right? This, the second order derivative is actually, you can consider this as a Laplace transformation. This is a new function and derivative. Right? So if you say this is a f small ft, then the following: s of f over s minus f over 0, right? But this is s times sy over s minus y over 0 minus dt dy 0, right? So s square y over s minus s y over 0 minus dt dy over 0. And then you can continue. Third order. Dt square s cube y over s minus s square y over 0 minus s dt dy over 0 minus dt square y over 0. So we can continue this process, right? So maybe I can leave this as homework. You can check at home. let's construct a table then. Then, for example, if we have a1 dt squared d square y, a2 dt dy, a3y is ft. Then, taking a Laplace transformation, of the above, what do we get? a1 s square y over s minus s y over 0 minus dt dy over 0 plus a2 s y over s minus y over 0 plus a3 y over s is f over s, right? So we have a1 s squared, a2s, a3 y over s minus a1s y over 0 minus a1 dt dy over 0 minus a2 y over 0 is equal to f over s. Copy and delete. And next page, paste. I'm going to move this. So that means, so therefore, a1 s squared plus a2 s a3 y over s is equal to a1 s y over 0 minus a1 dt dy over 0 minus a2 y over 0 plus f over s. So therefore y over s is something like a1 s squared plus a2s a3 over a1 s y over 0 minus a1 dt dy over 0 minus a2 y over 0 plus f over s. And then from this you can find the y of t. How? How can you find the f of t? From the lookup table. So we have to construct a table of functions first. So we are going to consider only polynomial, exponential, and sinusoid cases. The first case, f of t exponential lambda t. The Laplace transformation of exponential lambda t is exponential minus st times exponential lambda t dt, right? So that is exponential minus s minus lambda t dt minus s minus lambda exponential minus s minus lambda t 0 towards infinite s minus lambda, right? So once we have this table, then you can find that s minus lambda we know this is lambda t, right? So consider the following example. Just copy one thing at a time. Previous result. Assuming that we have the following differential equation, 3, 2y is equal to 0, with the following condition, y0 is 1, dt dy 0 is 0. So Laplace transformation of dt dy t is what? S of ys minus y of 0 is s of ys minus 1, right? How about dt square y of t, s square y of s minus s y of 1 minus dt dy 0 is s square y of s minus s, right? So the Laplace transformation of equation 1 becomes s square y of s minus s 3 times y of s minus 3, right? Plus 2y of s is equal to 0. That means s square plus 3s plus 2 y of s is s plus 3, right? That means maybe I'll let you copy this. very easy way of solving ordinary differential equations with the constant coefficient. Okay. So y over s is actually s squared plus 3s plus 2 over s plus 3, right? Let me check. So that means s plus 1, s plus 2 over s plus 3. You can put actually a over s plus 1 plus s plus 2 over b, right? So we already know the solution, right? So y of t, a times exponential minus t plus b times exponential minus 2t, right? So how do we differ? So we need to determine the coefficients a and b, right? We still need to determine a and b. So actually, you can solve this by partial fraction. So s plus 3, s plus 1, s plus 2 is a, s plus 1, b, s plus 2. So how do you determine a? This is actually I discovered in high school. So we actually you can use a partial fraction for solving this, but I found a better method in high school. That is, you just multiply s plus 2 and set s equal to minus 2. Let's say. Then we have s plus 1, s plus 3 equal to s plus 1, oh no, p. P. A times s plus 2 plus p, right? So set s equal to minus 2, what do we have? Minus 2 plus 1 minus 2 plus 3 is equal to p is 1. Determine a, multiply by s plus 1 and set s equal to minus 1. So that is s plus 2, s plus 3, s equal to minus 1 is equal to 1, 2, equal to a. So a is equal to 2. Well, in this case, it's very easy to check. So we have a equal to 2, b equal to 1. Let's check this. I made something wrong. Minus 2. Oh, so b must be minus 1, right? Minus 1, 2. b equal to minus. S plus 3, s plus 1, s plus 2 is equal to s plus 1 over a plus s plus 2 over b. Same as s plus 1, s plus 2, a times s plus 2 plus b times s plus 1 is equal to s plus 1, s plus 2, a plus b, s, let me see, plus 2a plus b. So a plus b is equal to 1. 2a plus b is equal to 3. So a is 2, b is equal to minus 1, right? So this method actually works. So you can utilize this when you find the partial fraction expansion. Maybe we can take a break for 5 minutes. The another question is, what is Laplace transformation of sine and cosine? Of course, you can do this. You can calculate. Probably you have done that in high school, right? If you have a sine or cosine, then what you need to do is you do the partial integration twice. I will give you the much easier method. Using from the Euler's formula, we have cosine t plus I sine t. This is Euler's formula. So, Laplace transformation of exponential it is 0 to infinite exponential minus st exponential it dt is s minus it dt is s minus I exponential minus s minus I 0 to infinite is actually Laplace transformation of cosine t, Laplace transformation of I sine t is cosine t plus I Laplace transformation of sine t. Is 1 over s minus I is equal to Laplace transformation of cosine t Laplace transformation of I sine t. Which is s minus I, s plus I, s plus I, right? And this is s squared plus 1, S plus I. The same as this. S squared plus 1 plus I 1 over s squared plus 1. The same as Laplace transformation of cosine t plus I Laplace transformation of sine t. So what do we have? Therefore, Laplace transformation of cosine t is s squared plus 1. Laplace transformation of sine t is 1 over s squared plus 1. So maybe it's about time to show that Euler's formula is true, right? Because I just assume that it is true. So let's check that. So I'll let you copy. So exponential theta. Anybody remembers Taylor's formula? 1 plus theta square plus, no, not theta square. 1 over 2 factorial theta square plus 1 over 3 factorial theta cube plus something like that, right? So if theta is it, what happens? Exponential it is 1 plus it plus 2 factorial it square plus 3 factorial it cube plus. So 1 plus it plus 1 over 2 factorial it square is minus t square, right? Plus 1 over 3 factorial minus it cube. So that is 1 minus 2 factorial t square plus I times t minus 3 factorial t cube plus. Anybody remembers Taylor formula for cosine? One minus t square over 2 factorial over 4 factorial over t fourth, right? How about sine t? T minus 3 factorial over t cube, 5 factorial over t5, something like that, right? So that means this is actually cosine, and this is sine, right? So therefore, exponential it is equal to cosine t plus I sine t, right? So we have the Euler's formula. now you know that, right? You don't have to memorize because so Euler discovered this formula in 17 something, 18 something, right? 19th century. So Euler's formula is very useful formula. How about sine omega t, cosine omega t? So in this, now we consider exponential I omega t. It's the same as before. This is cosine omega t plus I sine omega t. So Laplace transformation of the above. So Laplace transformation of exponential I omega t is minus st s minus I omega over 1. 1 over s minus I omega. So 1 over s minus I omega is actually s minus I omega, s plus I omega, s plus I omega is s square plus omega square plus s plus I omega is same as Laplace transformation of cosine omega t I times Laplace transformation of sine omega t is so Laplace transformation of cosine omega t is s over s square plus omega square, and Laplace transformation of sine omega t is omega over s square plus omega square. So I'm going to ask you another homework. Okay, I'll let you copy this first. So actually you can obtain Laplace transformation of sine and cosine using Euler's formula very easily, right? But if you do the original integral, also you can get the same result, right? So those are the following homeworks. Oh, today is okay. I think the screen is still there. It's not turned off. Last time it was turned off every hour. But I think we are lucky. Somehow. So this is homework. Show that you can do this, right? It's actually a high school problem. You integrate using partial integration by twice. 부분적분 2번 하면 되죠? Very easy. using partial integration twice. Just go back to your high school days and do the partial integration. I think maybe just one page for each paper. Maybe half an hour for two problems. But this, yeah? This is homework. Just do at home. You don't have to turn in. But it's going to be a good practice. And you will discover how convenient is the Euler's formula. So let's consider another example. Copy. Example, maybe same problem. The t square yt plus 3 dt dyt plus 2yt is equal to, say, sine omega t with the y. Okay, you can decide the initial condition. Y0 is equal to? Okay, 0. How about zero? Okay, it's good. That's a very good problem, right? If you have a two initial condition 0, that will simplify the solution quite a bit. So, taking a Laplace transformation of 1, what do we get? We have s squared ys, because the rest are 0, right? Plus 3s y over s plus 2y over s is s squared plus omega squared over omega, right? So s plus square 3s plus 2. It's not a very easy problem, though. S squared plus omega squared plus omega. So y over s is s plus 1, s plus 2, s plus omega squared over omega, right? Okay, let's modify the problem a little bit for your convenience. Just simply 1. Much better, right? So just 1. Plus 1, 1. Plus 1, 1. Right? So, you need more time to copy, or I can move on? I simply changed omega into 1 because I don't want to, I want to make this problem as simple as possible. So we can try the partial fraction. Okay, so y over s is actually s plus 1, s plus 2, s squared plus 1 over 1. So this is actually s plus 1 over a, s plus 2 over b, s plus 1 cs plus d, right? Using partial fraction. So a, what do we do? You multiply by s plus 1 and set s equal to minus 1, right? As before. So s plus 2, s squared plus 1 over 1, s equal to minus 1 is same as 1 plus 1 over 1 is actually a, right? So a is 1 over 2. For b, you multiply by s plus 2 and set s equal to minus 2, right? So we have s plus 1, s squared plus 1 over 1 is equal to minus 2 is minus 1. This is 5. S squared plus 1 is 5, right? Is equal to b. So b is minus 1 over 5. Now the tricky part is finding c and d. So here's minus 1 over 5. S plus 1, s plus 2, s squared plus 1 over 1 is actually a, s plus 1 plus b, s plus 2 plus s squared plus 1, cs plus t. So we first multiply by s minus I on both sides and set s equal to I. See what happens. So we have s plus 1, s plus 2, s plus I, because s squared plus 1 is actually s plus I, s minus I, right? S plus I over 1. You set s equal to I is what? We have 1 plus I, 2 plus I, 2I, right? Over 1. Is equal to 1 plus 1, 4 plus 1, 2I times 1 minus I, 2 minus I, right? So this is 2 times 5 times 2I over, this is 2 minus 2I minus I minus 1, denominator. So 1 times 2 minus 2I minus I, and this is minus 1, right? So we can organize this as 20I times 1 minus 3I, right? Is actually 20 times minus I minus 3, right? It's same as this. We have S plus I and CS plus D S equal to I. So this is 2I times CI plus D. Actually, maybe this is better. So this is 20I times 1 minus 3I. So we can actually decide C and D at the same time. So CI plus D is actually 10 over 1 minus 3I. So D is 1 over 10. C is minus 10, 3 over 10. Right? So we have A was A 1/2, B was what? Minus 1 over 5. C is minus 3 over 10. D is 1 over 10, right? We don't have enough space. So see, you need the copy. So maybe I'll just copy this. Copy. Okay. So that means so y of s (1 over 2) s plus 1 minus 1 over 5 s plus 2 minus 10 over 3 s over s squared plus 1 plus 1 over 10 s squared plus 1, right? Let me check. Y over t 1 over 2 exponential minus t minus 1, 5 exponential minus 2t minus 3 over 10 cosine t plus 1 over 10 sine t. Definitely, if you find the table, you can solve this differential equation very easily, right? So for the lookup table, we only covered the exponential and sine and cosine. Maybe polynomial too. Maybe we can have the polynomial tables too. copy, just in case. So as long as the coefficient is constant, then this Laplace transformation is one of the most convenient methods solving inhomogeneous ordinary differential equations. So typical example is something like RLC circuit, right? You have CL. So if you have some function input as some sine sinusoidal function as input, then the Laplace transformation is one of the easiest way, convenient way solving this circuit problems. And I think in the electric circuit class, maybe Laplace transformation will be covered soon, maybe before the final exam. So what is the text that you are using for Laplace transformation and circuit theory? It must be quite different from the book I used when I was a sophomore. Okay, about when ft is equal to 1, then Laplace transformation of ft is one over s, right? How about Laplace transformation of t? You can actually calculate using partial integration, right? But there's a simpler method. How do you obtain t here? I mean, of course you can integrate this using partial integration. What if we differentiate this by s? What do you get? What is different? But if we differentiate exponential minus st by s, what do you get? Minus t times exponential minus st, right? So this is actually the same as right? If we differentiate this exponential minus st by ds, then you obtain t, right? And integration is over t, but you differentiate by ds, you can move this out. And this is turns out to be 1 over s. So this is minus dst 1 over s. 1 over s squared. Very convenient, right? You don't have to do the partial integration anymore. Just differentiate by s. Right? I also discovered this formula in high school. Because I was kind of lazy doing, I really hate doing partial integration many times. So I tried to find if there's a simple way of doing this. This is one of the methods I found. So what about t squared? Laplace transformation of t squared is again minus dsd Laplace transformation of t, right? Minus dsd times 1 over s squared s cubed over 2. So we can continue actually Laplace of Tn s to the n plus 1 and factorial. So maybe we can show this by using homework, using induction. So now we have finally a table, lookup table. We have TFT, Laplace transformation of FT, and exponential lambda t, s minus lambda, right? Cosine omega t, s over s squared plus omega squared, sine omega t, omega s plus omega squared, 1 over s, t, 1 over s squared, tn, n factorial, s n plus 1. I think these are probably the lookup table you need most for solving the differential equations arising from the circuit theory, circuit analysis. Most importantly, I think exponential and sine and cosine will be the only case you need. And so I'm thinking about stopping here today and continue next week. What do you think? Okay? So no more surprise quiz next week. You already got it, 10 points.